Hello, welcome back. To wrap things up, I'd like to consider one final example where we're going to try and use these Lyapunov techniques to study stability of a limit cycle rather than an equilibrium point. This is very much going to be kind of a special case. Doing this in general, we're not really going to look at methods for doing that, but we're just going to look at this special case, and hopefully it will help reinforce some of the ideas based on the Lyapunov functions and Lassalle's invariant set theorem that we saw before in a kind of a slightly different context. So what's the problem we're going to look at? We're going to study our simple polar coordinate limit cycle problem, where we had a system expressed in polar coordinates. We had d by dt of r theta dot, and then here we had r 1 minus r squared, and we had theta dot is equal to 1. And if you remember, we saw this system before, and when we plot its phase portrait in Cartesian coordinates, so here we've got x1 and x2, and our polar coordinates r and angle theta, we had the unit circle was of particular importance. So this is a circle of radius 1. And then we found that the trajectories were all tending to end up on this, they ended up on a limit cycle which was exactly equal to the unit circle. And I might have got the direction we're going around the circle inconsistent. But this is what happened when we had this particular system. And now we would like to use our Lyapunov and Lassalle type ideas to prove that all trajectories tend to this limit cycle. So what do we need to do? Well, we need many of the same ingredients. We need a Lyapunov function. We need some domain, omega, to conduct our analysis. And then we need to check v dot. And we do all of these things in the same way that we did when studying equilibrium points. And we'll just see a few subtle changes. So let's start by picking what set omega we want to use. We could go for global results here, but we'll maybe be slightly less ambitious. So we'll look at the set of points which, when written in polar coordinates, have radius r less than some big number r, just to keep our domain bounded. And we'll have angles between 0 and 2 pi. So what does that mean? Well, we just have some huge circle here with radius big R, and this is our set omega. And we're going to try and study stability on, well, we're going to try and prove that this limit cycle is stable when we start anywhere in this set omega. And to do this, we need a Lyapunov function, and we're going to pick v of our state, which is r and theta, and we're going to say that this thing is equal to 1 minus r squared, and I'm going to multiply the whole thing by a quarter. We're not going to bother justifying where this comes from. I think you will maybe begin to get an idea when you start to see the calculations evolve, and that is sort of an important lesson in the Lyapunov functions. There's really an element of the dark arts in how you find them. You have to sort of, you build some familiarity through looking at examples, and you sort of end up with this dictionary of common Lyapunov functions, and typically you're restricted to just searching over your dictionary and hoping for the best. So I mean, they're nice methods, and when they work, they allow you to prove stability, but there's no sort of guaranteed procedure, or at least not one that I'm aware of, that will find Lyapunov function for a general problem. So what do we need to do? So this is our Lyapunov function, and why, first of all, why have we chosen this Lyapunov function? Or what is some motivation behind it? Well, we see that if we put in r is equal to 1, the Lyapunov function is equal to 0, whereas for all other values of r, it's bigger than 0. So this is defining an energy function which has got no energy on our limit cycle. So our limit cycle here, this is the contour v of x is equal to 0. And then for different values of r, we just get different contours of our Lyapunov function. So this is v of x equal to, say, 1. And you see the further and further we go out, the bigger and bigger the contours. So this is sort of our equivalent to point 1. We have that v of x is equal to 0 for x on the limit cycle. That's good. And we also have our second Lyapunov type property. We have that v of x is bigger than 0 for all x in omega, not on the limit cycle. So everything's sort of set up to work. We have these level sets. They are getting bigger and bigger. And now if we can prove that v dot is strictly decreasing, that means that we'll be, whenever we're on one level set, we're guaranteed to move to one of lower energy, and we'll keep on going and going and going until we end up on the level set of 0 energy, which corresponds to our limit cycle. So we want to do exactly what we used to do with point 4. So point 3 was just going for stability. Point 4, we're going for asymptotic stability. So we want to prove that v dot is less than 0 for all x in omega, not on the limit cycle. And if we can do this, then we're guaranteed to end up on this set here. So how do we do it? Well, we just have to find v dot, and we do that in exactly the same way that we did before. So v dot is equal to grad of v dot producted with f, and so this is dv by dr, dv by d theta. So these are our two state variables. So this is the grad of v, and we dot product that with our dynamics, which are given here. And we have r 1 minus r squared 1. So what do we get? Well, dv by dr, so we need to differentiate this with respect to r, and now you start to see a little bit why, a little bit of the reason why we chose this particular v. Well, this is equal to minus r1 minus r squared. And nothing here depends on theta, so this is 0. Okay, fine. And so we then dot product that with our dynamics, which is r1 minus r squared 1. And what do we get? Well, if we do that, we get minus r squared 1 minus r squared. And this is less than 0 for all x in omega, not on the limit cycle, which is exactly what we were trying to show. So this now guarantees that we start on any level set in this region omega. If that level set has got energy or the value of the Lyapunov function larger than 0, we're guaranteed to move towards one with lower value of the Lyapunov function, meaning that eventually will collapse onto our unit circle as required. So a kind of an extra bonus doing some limit cycle stuff with the